In section 3.1, we look at quadratic functions. This should be a review topic for many of you. We say a function f is a quadratic function if it can be expressed in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and the number a cannot equal 0. The domain of a quadratic function is the set of all real numbers. And below here, you'll see 3 example graphs of quadratic functions. We call the shape of the graph of a quadratic function a parabola. And parabolas are these sort of soft V-shaped graphs. Some people call them a U-shaped graph. And you can see that it can either open upward, like this one here, or it can open downward, like this one here. Quadratic functions will typically have 2 x-intercepts. So we can see that we have x-intercepts here for this one. And for this next one, you can see that you have x-intercepts here. But they don't have to have x-intercepts. And you can see in this third example that it does not cross the x-axis. All parabolas have a point called the vertex, and that vertex is sort of the middle point of the parabola. And that point will either be the highest point on the graph, as it is here, or it can be the lowest point on the graph, as it is here. And you can also see that we have a vertex in this one. And the vertex is probably the most important aspect of a quadratic function. So we'll be talking about how you can identify that vertex. And then the other important aspect is the x-intercepts. And we'll be talking about that as well. So now I want to talk about what is called a quadratic function in standard form. So instead of expressing the quadratic function as we did on the previous page, you can also rewrite it in this form, where it's a times the quantity x minus h squared plus k. And this is what we call standard form. Now, the nice thing about this form is that when it is in this form, we can easily identify the vertex of the parabola as being the point hk. Also, we know that if the number a here is a positive number, the parabola opens upward, and that vertex is going to be the lowest point on the curve, like you see here. And if that number a is a negative number, it will open downward, and the vertex will be the highest point on the curve. So the big question is, if you don't have a quadratic function in standard form, how do you put it in standard form? But first, let's start with a simple example. So in this example, they want us to graph the quadratic function using transformations. We don't have to actually use transformations for this one. I will talk about that a little bit. But I do want to point out that this parabola is in standard form. We have the number -2 multiplied by the quantity x minus 1 squared, and then plus 3. So because it is in standard form, we can easily identify the vertex. So let's bring in that formula. And you should see that here we have the quantity x minus h squared, but over here we have positive k. That matters. When you're trying to identify the vertex, what the negative means in front of the h is that you need to take the opposite of the value that you see to find the x-coordinate of the vertex. And the positive k, you take the same sign as what you see. So what that means here is when I'm looking for the vertex, you can see I have a -1 here. That means the coordinates of this vertex is going to be +1 because we have to take the opposite of that. But then the y-coordinate of the vertex is +3. So we take the opposite of this coordinate, but we leave this one alone. So that is the vertex. We also know that this parabola is going to open downward. because we have a negative value of a in front of the parentheses there. And with that, we can actually graph the parabola quite easily. So we have a vertex is the point 1, 3, which is this point right here. And I'll write the letter V next to it to stand for vertex. And then now we just need to get some additional points on the function. So to do this, we can just make a table of some values. We have 1, 3 in the middle. And then to get some additional values here, some additional points, I will just pick some x values to the left and to the right of x equals 1. So a couple of values to the right would be x equals 2 and x equals 3. And to the left, I can pick x equals 0 and x equals -1. And then we will plug those values into the function. So for example, if I want to know what is f of 3, I'm going to plug 3 in for x. So that gives us -2 times 3 minus 1 squared plus 3. This is -2 times 2 squared plus 3, which is -2 times 4 plus 3. And this is -8 plus 3, which is equal to -5. And so the y-coordinate when x equals 3 is -5. And we can do the same thing for the other points as well. So I will skip the work, but you can plug in these other values of x. And when you do, you will get x equals 1. Y equals 1 when x equals 2. You will get y equals 1 when x equals 0. And you will get y equals -5 when x equals -1. And with these points, we can simply plot them on the graph here. So here's the point 3, -5. Here is the point 2, 1. And then here is 0, 1. And finally, -1, -5. And from there, I can sketch the graph by basically just connecting these points, make it nice and smooth. There should be no sharp edges on this graph. And that is what the graph looks like. Now, I didn't use transformations to do the graph, but this is just as effective. And it also asks, what is the vertex? Well, we already identified the vertex, okay? Now, let me talk briefly about how you would use transformations to do this graph. To use transformations, we would start with what we call the parent function. And the parent function for this function is f of x is equal to x squared. And we know that x squared passes through the point 0, 0, 1, 1, 2, 4, -1, 1, and -2, +4. And so it has this shape. So when we're graphing this function here, we're going to do the transformation step by step. So first of all, we would just ask, what would the function f of x equal x minus 1 squared look like? And we should remember that when you have x minus 1, that is going to shift the graph 1 unit to the right. So if I take this graph and shift it over 1 unit to the right, the vertex will be here, and the parabola will look the same. So let's go ahead and sketch that. All right, so that's what that one looks like. Now you might be wondering, well, how did I know to start with that? Well, when you're graphing using transformations, you identify your variable x, which is here, and then you take the first thing that is closest to it, which is the -1. So if you were to plug in a value for x, subtracting 1 would be the first thing you would do. So that's why I looked at that transformation first. So now once we know what x minus 1 squared looks like, the next thing we'll do is we'll say, well, what does multiplying it by -2 make it do? Well, multiplying it by a negative is going to reflect this graph over the x-axis. Okay, so if we had the function f of x is equal to negative x minus 1 squared, we would simply flip these points over the x-axis, which would look like this. So this is what f of x is equal to negative quantity x minus 1 squared would look like. So then the next thing we want to understand is, well, what does the 2 do? So instead of having negative, we have negative 2 times x minus 1 squared. Well, the 2 does a vertical stretch. So what that means is all the y values are going to be twice as tall as they appear now. So down here, when y is equal to negative 1, twice as tall is going to make it be at negative 2. So that point will move to here. When we are at the point y equals negative 4, twice as tall means that it will be down at negative 8. So if we make all of these points twice as tall as they used to be, we get a graph that looks like this. And then finally, we want to know, what does adding 3 to the graph look like? So f of x equals negative 2 times x minus 1 squared plus 3. Well, the 3 is going to move it up 3 units. So now we just take every point on this curve and we lift it up 3 units. And when we do that, we get this point here, this point here, this point here. And then down below, when you move these points up 3 units, you get these points here. And if we sketch that graph, we get the following. And this is the same graph that we had a few minutes ago. Now, in my opinion, it's just quicker to graph it by finding the vertex and then finding 2 points to the right and 2 points to the left of the vertex. So I personally like the first method a little bit better, but this method also works. Next, we want to talk about how to write a quadratic function in standard form by completing the square. So in this problem here, we have the function f of x is equal to x squared minus 8x plus 4. And we want to write it in the form that you see here. So what we need to do is complete the square. So first of all, notice that you have a 1 in front of x squared. This is good, makes the process a little bit simpler. So to complete the square here, we are going to first just take that positive 4 and move it over to the right a little bit. And then to complete the square, we identify the middle number here, which is negative 8. We divide that number by 2 and we square it. And this gives us negative 4 squared, which is positive 16. And that number is the number that we add here to complete the square. But when you add 16, you have changed the equation. So off to the right here, we are going to put minus 16 because these two numbers cancel each other out, thus giving us the equation that we started with. But we're not going to actually cancel them. We're going to leave them in the equation, and we're going to factor this, and then we'll have that. So when you factor this, you get x minus 4 times x minus 4, and then positive 4 take away 16 is negative 12, and this is x minus 4 to the second power minus 12. And now we have put this quadratic function in standard form, and the vertex is positive 4, negative 12. In the next example, we want to do the same thing. In part A, we want to use completing the square to rewrite the quadratic function you see here in standard form. And then we'll identify the vertex, and we'll talk about whether it reaches a maximum or minimum value at the vertex. So to start with, we have f of x is equal to 3x squared plus 12x plus 8. And I want to point out right away, notice that we do not have a 1 in front of the x squared. So in this case, what you want to do is factor the 3 out of only the first two terms. So when I pull the 3 out of x squared, or out of 3x squared rather, we get 3 times the quantity x squared. Plus, when you pull a 3 out of 12x, you get 4x. And then we're going to leave a space here for completing the square. And then we still have the plus 8 on the outside of those parentheses. Now on the inside of the parentheses, notice you have a 1 there, which is important. we take that middle number 4, divide it by 2, and square it, and this gives us 4, and we are going to add 4 to complete the square. Now, once you add 4 to complete the square, you have to compensate for that on the outside by getting rid of that plus 4. But here's the tricky part. Most students, what they will do is they will put a minus 4 out here. But that is actually incorrect, because when you add 4 here, that 4 is also being multiplied by 3. So even though you may have written plus 4, you actually added 12, because 3 times 4 is 12. So to compensate for that, we have to subtract 12 on the outside. Once you get past that step, then we're going to go ahead and factor. So this is 3 times x plus 2 times x plus 2. And then positive 8 and negative 12 is negative 4. And this simplifies to 3 times x plus 2 quantity squared minus 4. And so we have completed the square to write this in standard form. Now, the second part of this problem asks us to identify the vertex. Well, to get the vertex, remember you have to take the opposite of this number, so that will be negative 2. And then this number here you leave as is, that is negative 4. So there is our vertex. And then finally, they ask the question, does f reach a maximum or a minimum value at this vertex? So the only thing that matters here is just an understanding of whether your parabola opens up or whether your parabola opens down. When it opens up, you have a minimum value at your vertex. And if the parabola opens down, you have a maximum value at the vertex. And we know that this parabola opens up since a is equal to 3 and 3 is positive. So I'm identifying the number a here, right, in front of the parentheses. If that number is positive, we know it opens up. And if it opens up, we know that the vertex is at the minimum value, right? Because in that case, the vertex is at the bottom of the curve. So that's the minimum value of the curve. Next, we're going to talk about a formula for finding the vertex of a quadratic function. So another way to get the vertex without having to complete the square is you simply take your quadratic function in the original format, ax squared plus bx plus c, and you can find the vertex by using the formula given here. So remember, we call h and k the coordinates of the vertex. So the x coordinate of the vertex, which we call h, is given by negative b over 2a, and the y coordinate of the vertex, which we call k, is given by c minus b squared over 4a. And another way to remember it is just know that you have to plug in negative b over 2a for x to find the y coordinate. Now, the way you get this formula is through completing the square. And I might post a second video on that just for those who are interested, but I will leave that out as a part of this video. Otherwise, this video will get a little bit too long. One other thing to point out when you have a quadratic function is that there's a vertical line that goes right through the vertex, and that line is what we call the axis of symmetry. And the equation for that line is always x equals h, where h is just the x coordinate of the vertex. Let's take a look at an example. So in this next example, we have the function f of x is equal to 2x squared minus 8x plus 1. And we want to find the vertex and the axis of symmetry of this graph. And we don't have to graph it to do these things. Instead, we know that to find the vertex, we know that the x-coordinate of the vertex, which we usually call h, is given by the formula negative b divided by 2a. So we need to identify a, b, and c. So in this particular function, a is 2, b is -8, and c is 1. And so to find the x-coordinate of the vertex, we just have to take negative b, and b is -8, so that's going to be -8 divided by 2 times a, and a is 2. This is 8 divided by 4, which is equal to 2. So we know that the coordinates of the vertex are going to be 2, and then we still have to find the y-coordinate. Now, to get the y-coordinate, it was a formula for that on the previous page, but it's much easier when you're finding the y-coordinate to just take your x-coordinate and plug it into the function. So we just need to do f of 2, and when you plug 2 into the function here, you are going to get 8 minus 16 plus 1, and this is equal to -7. So the vertex of this parabola is 2, -7. Now, what is the axis of symmetry? Well, remember, the axis of symmetry is nothing more than a vertical line, so it's going to have an equation x equals, and then we just take the x-coordinate of the vertex. So the axis of symmetry is x is equal to 2. Next, we're going to talk about the real zeros of a quadratic function. So the real numbers x at which f of x is equal to 0 are called the real zeros of the function f. Now, this is not just true for parabolas, it's true for all functions. Basically, what we're talking about here, if you just think of a graph, the real zeros are the values of x where the graph crosses the x-axis. So real zeros really is the same thing as the x-intercepts. Let's take a look at this example. So in this example, we want to find the x-intercepts of the parabola associated with the function that you see here. Also, find the real zeros of f. So understand that when they ask you to find the x-intercepts or the real zeros, they are asking you to find the same thing. So our function is f of x equals 3x squared minus 5x minus 2. To find the zeros, or the x-intercepts, what we do is we set f of x equal to 0. So we're literally going to let f of x be 0. If you do that, you get the equation 3x squared minus 5x minus 2 equals 0. And now we just have to solve that quadratic equation. And we've already talked about how to solve quadratic equations. You can use factoring, which is what I'm going to use here. So 3 times -2 is -6. Take the middle number, which is -5. Find two numbers that multiply to give us -6 and who add to get -5, and we have -6 and 1. Then to use our magic x factoring technique, we know we're going to have x minus 6 and x plus 1. But because we have a 3 here, we have to divide each of those numbers by 3. And this simplifies to x minus 2 for the first factor. And then the 3 here goes in front of the x and gives us 3x plus 1. And now I just set those equal to 0. So x minus 2 equals 0, which means x equals 2. And 3x plus 1 equals 0, which gives us x is equal to -1/3. So the real zeros of our function are x is equal to 2 and also -1/3. And then if they ask for the x-intercepts of our function, the only difference here is x-intercepts are points. And so you would write this down as 2, 0 and -1/3, 0, right? Because x-intercepts are the points where it crosses the x-axis, which means the y-coordinate is 0. So the answer might look a little bit different for each of these, but just understand that the process is exactly the same. Next, we want to talk about graphing a quadratic function using the vertex and the intercepts. So to get a decent picture of a parabola, you can just find the vertex and the x and y intercepts. And that will work as long as it has x intercepts. But we'll go ahead and go through the process here. So for this particular quadratic function, they want us to find the maximum value of f. So notice that you have a quadratic function. It's a parabola that opens down because a is -3. So it does make sense to find the maximum value of f. Basically, to do this, we need the vertex. To find the vertex, we know that x is equal to -b divided by 2 times a. b in this problem is -6, so we have -6. Divided by 2 times a is -3, so that's 2 times -3. And this gives us 6 divided by -6, which is -1. And then the y-coordinate of the vertex, we are now going to take the value x equals -1 and plug it into the function. And when we do this, we get -3 times 1 plus 6 plus 2, and this is -3 plus 8, which is equal to 5. So the vertex for this parabola occurs at x equals 1 and y equals 5. Now, they didn't ask for the vertex. They asked for the maximum value of f. The maximum value of f is the y-coordinate of the vertex, right? Because the y-coordinate is how high the function gets. So the max value is 5. The x value of the vertex only tells you where the maximum value occurs, but it doesn't tell you what the maximum value is. And we'll look at a graph in just a bit here, just to bring everything together. In part B, they want us to find the axis of symmetry. Well, again, the axis of symmetry is nothing more than x equals the x-coordinate of the vertex, which we know is -1. So that's our axis of symmetry. For the next part, they want us to find the x-intercepts if they exist. So to do this, we let f of x be equal to 0. And if we let f of x equal 0, we get 0 equals, there's our function, -3x squared minus 6x plus 2. Now, when solving a quadratic equation like this, you should always want your leading coefficient to be positive. So what I'm going to do here is multiply both sides of the equation by -1. Multiplying by -1 changes all the signs, and this will allow us to factor this a little bit more easily. So let's go ahead and look at that factorization. Hopefully it will factor. We have 3 times -2 is -6. In the middle, we have +6. And we have to try to find two numbers that multiply to give us -6 and add to give us +6. And there are no numbers that will do that, right? There are no whole numbers that will do that. So it looks like to find our x-intercepts here, we are not going to be able to use factoring. So if factoring fails, you need to remember that you can use the quadratic formula. Quadratic formula tells us x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a. And so for this particular example, we have -6 plus or minus the square root of 6 squared minus 4 times 3 times -2, all divided by 2 times 3. And now we just need to go through and simplify this. So I will do this quietly because we have already discussed how to do this. But we end up getting -6 plus or minus the square root of 60 divided by 6. And you can simplify the square root of 60. You can pull out a 4, and the square root of 4 is 2. So we get 2 radical 15. And then you can cancel a 2 with the top and the bottom, and we get two values for x. We have negative 3 plus the square root of 15 divided by 3, and we have negative 3 minus the square root of 15 divided by 3. And these are the values of your real zeros or your x-intercepts. And then you could also approximate these values, which is kind of useful if you're going to be doing a graph. So let's go ahead and get the approximations to those. And when we do that, we get approximately 0.29 and negative 2.29. And again, we'll come back to that. Let's go ahead and do the next part, part D. Find two additional points on the graph and then sketch the graph by hand. All right, so to find two additional points on the graph, we just need to plug in a couple of other x values. So we already know that when x is negative 1, we know that y is 5. That was our vertex. We also know that our x-intercepts occur at negative 0.29, positive 0.29 and negative 2.29. So to get a couple of extra points on the graph, maybe I'll just plug in x equals 0. That's an easy one to plug in. If you plug in 0 to your original function, f of 0 is going to be 2. And then maybe I'll just plug in x equals positive 1. If x equals positive 1, f of 1 is going to be negative 3 times 1 squared minus 6 times 1 plus 2. This is negative 7. All right, and now we should be able to take these points along with our x-intercepts and sketch the graph. So let's bring in an axis. So here we are. Let's go ahead and graph these points. We have the point 0, 2. We have the point negative 1, positive 5, which is our vertex. We have the point positive 1, negative 7. And we also know that there is an x-intercept at 0.29, which is right about here, and another x-intercept at negative 2.29, which is right about there. And then the other thing we know is that the axis of symmetry is the line x equals negative 1, which is this line right here. Now, the reason I bring this in is because when you have an axis of symmetry, we know that the graph is symmetrical on both sides of that line. So if this is a point on the graph, we know that this is also a point on the graph. So we can add that in. Likewise, down here, if this is a point on the graph 2 units to the right of the axis of symmetry, then there should be a point 2 units to the left. And so we can add that point to the graph. And once you do all that, then you can sketch the graph and get a relatively good picture of what this function looks like. All right, and there it is. Now, the last part of this problem, they say to use the graph to find the intervals where f is increasing or decreasing, and also to find the range. Okay, so let's answer these questions. So where is the graph increasing or decreasing? Well, as you read the graph from left to right, it's increasing when the graph is going up. So it is increasing for this portion of the graph. So that would be all the values of x that are less than negative 1. So we will say that this graph is increasing on the interval from negative infinity up to negative 1. And it is decreasing after that. So it is decreasing on the interval from negative 1 to infinity. Finally, what is the range of this graph? Well, the domain we know is all real numbers. That is always the case for quadratic functions. The range is the set of y values that are covered by this graph. So you can see that y equals 5 is the highest point on the function. So the range is going to be all the y values 5 or below. So to write that in interval notation, we will say the range is all the values from negative infinity up to 5, including 5. All right, this next example is just a twist on what we just did. Here they say, find a possible expression for a quadratic function f of x that has zeros x equals negative 3 and x equals positive 1. So what you do here is you just work backwards. If x equals negative 3 is a 0, notice that if you add 3 to both sides of this equation, you get x plus 3 equals 0. And if x equals 1 is a 0, subtracting 1 from both sides gives you x minus 1 is equal to 0. So your function f of x in factored form will be x plus 3 times x minus 1. And now if we just multiply this out, we get x squared plus 2x minus 3. So this is a possible quadratic function that has the zeros given to us in the beginning. Now, one other thing to notice here is that they don't ask for the answer. They ask for a possible expression for the quadratic function. So this was one possible answer, but you could have any other answer that has this as the main part of the quadratic function, and then you can multiply by any coefficient you want in the front. So for example, another possibility would be g of x equals 2 times x squared plus 2x minus 3. That would have the same x-intercepts, but would have a slightly different shape. And if you multiply this out, this would be 2x squared plus 4x minus 6. Okay, so that's another possibility. We could also do something like h of x equals negative 3 times x squared plus 2x minus 3. And if you multiplied this one out, you would get negative 3x squared minus 6x plus 9. And just to kind of show you, I'm going to bring in a graph of all three of these so you can see that indeed they have the same real zeros. So I want you to notice that in this graph here, this is the original function x squared plus 2x minus 3, the green graph here. Notice that it does have an x-intercept at x equals negative 3 and also x equals positive 1. G of x, which is 2x squared plus 4x minus 6, that is the purple graph here. And I want you to notice that the shape is different, but it does have the same x-intercepts as the first graph. And finally, negative 3x squared minus 6x plus 9 is this graph. Notice it is a parabola that opens downward, but it still has the same two x-intercepts. So changing the number a in front of the whole function here doesn't change the x-intercepts, it just changed the shape of the graph. So this is why there's more than one possible answer for this problem. Now, if you're asked to do a problem like this, it's usually easiest to just get your two factors and then multiply out those factors and just use this first answer. But I just want you to understand that there are other possible answers to this. And for our final example, we will look at an application. So here we have a problem on maximizing area. It says that traffic authorities have 100 feet of rope to cordon off a rectangular region to form a ticket arena, specifically for concert goers who are waiting to purchase tickets. Okay, so we have a rectangular area. I can draw a picture of this. So just basically a rectangle. That rectangle will have a width and a length. This will also be the width here, and this will be the length here. And it says to express the area of this region as a function of the length of just one of the four sides of the region. Okay, so for this rectangle, what I want to do is call the width x. So what I can do now is I can come in here and change this to x. So we don't know how wide it is, but we're going to say that it's x feet wide. And then we want to know, what is the length going to be? Well, to get the length, What we're going to do is use the fact that we know the perimeter of a rectangle is 2 times the width plus 2 times the length. We know the perimeter is 100 because they told us we had 100 feet of rope to make this rectangle in the first place. So perimeter is 100. And that's equal to 2 times the width. We already said the width is x, and then plus 2 times the length. So we can solve for the length here by subtracting 2x from both sides. This gives us 100 minus 2x is equal to 2 times the length. And then if we divide both sides by 2, we get the length is equal to 50 minus x. So what I did here is 100 divided by 2 and 2 divided by 2. So the length of this rectangle can be expressed as 50 minus x. So now we have both the length and the width expressed using the same variable. Now what they want us to do is express the area of this region as a function of this variable x. Well, we know the area of a rectangle is the width times the length. So that means the area of our rectangle is the width x multiplied by the length, which is 50 minus x. And this is equal to 50x minus x squared. And we can rewrite that as area equals negative x squared plus 50x. So here is the area as a function of one of the lengths of the side. In the second part, they ask us to find the dimensions of the enclosed region that will give a maximum area, and then determine what is the maximum area. So this is the part where you need to realize that your area function is a quadratic function. And if it's a quadratic function, we know that its maximum value is at the vertex. So what we need to do the second part to this problem is we need to find the vertex. Well, to get the vertex, we have a formula. X is equal to negative b divided by 2 times a. In this function, b is 50 and a is negative 1. And so negative b is negative 50 divided by 2 times a is 2 times negative 1. This is negative 50 divided by negative 2, which is 25. Now, the y-coordinate of the vertex, which isn't really called the y-coordinate, should be called the a-coordinate, because we express this as the area function. So our y-coordinate is an a-coordinate. But our a-coordinate is just going to be plug the x value into your function. So this is negative 25 squared plus 50 times 25. 25 squared is 625, so that's negative 625, plus 50 times 25 is 1,250. And when you add those together, you get 625. So to answer the question here, it says find the dimensions of the enclosed region that will give a maximum area. Well, the dimensions are given by x equals 25. So the width is going to be 25 feet, right? Because the width is x, and we know x is 25. And the length is going to be 50 minus 25, which is also 25 feet. So the dimensions are 25 feet by 25 feet. And the maximum area that you get from those dimensions, that was the y-coordinate of the vertex, which is 625 square feet. So this is an application of quadratic functions that we can use to find maximum or minimum values depending on the situation.